Hello, AP Chem. In our video for 13.6, I ran out of time to give you those concentrations for the different species. So chlorine is going to be 0.0075, NO is going to be 0.015, and NOCl is going to be 0.31. Hopefully you were able to get those answers on your own, but I wanted you to be able to check those as well. So today we're going to talk about LeChatelier's principle. And so what LeChatelier's principle is all about is a stress being applied to a system. So the equilibrium will shift in a direction that will relieve stress. So just like we don't like to be stressed, so we try to do whatever we can to relieve the stress, the system is going to shift so that it relieves the stress as well. This is what we call the bathtub hypothesis, and there are 4 changes that can happen to a system at equilibrium. So the first change is changes in concentration. An increase in concentration of your reactant is going to cause the equilibrium to shift to the right and form more products. So basically you're adding more reactants means you're going to form more products. Now if you have an increase in concentration of your product, now you have more product than you have reactant, and that's going to cause the equilibrium to shift to the left to form more reactants. When you decrease the concentration of your product, it will cause the equilibrium to shift to the right to form more products. So it's basically trying to replace those products that decreased or were removed or whatever. A decrease in concentration of the reactant will cause the equilibrium to shift to the left to make more reactants. So with these changes in concentration, it's important to note that a change in concentration of the reactant or product will not affect the value of K. So your equilibrium constant is going to be the same whenever these changes in concentration occur. And that's because these changes in concentration are not determining what the equilibrium concentrations are. They're more like the initial concentrations that we know to not have an effect on the equilibrium constant. So this image just kind of shows you initial equilibrium state. Q is equal to K, so our reaction quotient is equal to our equilibrium constant. And you can see that the products are kind of leveling off here. Well, here we're adding some of our H2. And when we add that, we need this to level back off. So right here in this gray region, Q is not equal to K. But as it shifts to make Q equal to K, then we return to equilibrium. So in the reaction of carbon monoxide and hydrogen to form CH3OH, if your carbon monoxide is increased, the forward reaction increases to reestablish equilibrium. Therefore, the quantity of H2 is going to decrease and the quantity of the product will increase. So basically, the more CO you add, the more H2 is also going to react, which is going to form more of this product. However, remember that your equilibrium constant stays the same. If the product is added to the system at equilibrium, the reverse reaction will increase to reestablish equilibrium. Therefore, quantities of both reactants, both carbon monoxide and hydrogen, will increase. So the value of the equilibrium constant, again, is going to become unchanged. So we still have the same reaction. We're adding more product. That's going to drive this reaction back to the left and increase the amounts of our products. But our K expression and our K value stays unchanged. Now, if we have continuous removal of the product from a reaction, this forces more of it to be produced according to LeChatelier's principle. Metabolic reactions as well as industrial processes make use of this effect to continuously make products in equilibrium reactions. So an example is acetic acid and ethyl alcohol form ethyl acetate. Continuously removing the product from the reaction is going to force more ethyl acetate to be produced. So these two examples, we have a generic equation A plus B forms C plus D. So now if we add more A or B, what is this going to do? Well, when we add more reactants, that's increasing the concentration of our reactants, is going to force our reaction to go to the right and make more C plus D, make more of our products. Now, if we remove some of our reactants, we're decreasing the concentration, so that's going to drive the reaction back to the left so that we can make more A or B in order to replace that. And then if we add our products to this, that's again going to drive our reaction to the left and make more of our reactants. If we remove some of our products, then we want to replace those. So we're going to drive the reaction to the right to make more of our products. So I'd like you to try this second example on your own. So go ahead and pause the video and see if you can figure out which direction the reaction is going to shift. Welcome back. So we start with the addition of nitrogen. Nitrogen is a reactant. That means that we are going to increase concentration of the reactants, and we're going to produce more of our product, which is NH3. Now, addition of NH3, we're increasing the concentration of our product, which is going to drive our reaction to the left and produce more of our reactants. If we add more H2, that is going to drive the reaction to the right and produce more of our product. And then if we remove some of our NH3, our product, we want to be able to replace that. So that's also going to drive the reaction to the right to produce more of the NH3. Okay, so the second change that can happen to your system is changes in temperature. Changes in temperature may easily be treated as changes in concentration if you think of heat as a product in an exothermic reaction and a reactant in an endothermic reaction. So remember, exothermic heat exits out of the system, so it would be on the product side. Reactant for endothermic, because endothermic reactions take on heat. So an increase in temperature on an exothermic reaction will cause the equilibrium to shift to the left. This also causes K to decrease. A decrease in temperature on an exothermic reaction will cause the equilibrium to shift to the right, and K will increase. An increase in temperature in an endothermic reaction will cause the equilibrium to shift to the right, and K will increase. A decrease in temperature of an endothermic reaction will cause the equilibrium to shift to the left, and K will decrease. So the changes in temperature is the only change that is going to affect your K value or your equilibrium constant. Now, I don't believe you have these examples in your notes, but you might jot them down so you have them for reference. So our first reaction, we have nitrogen and oxygen reacting to form nitrogen monoxide, and we are given our delta H is 181 kilojoules. And we want to determine what happens if we add heat or if we lower the temperature. So the first thing we need to do is we need to look at our delta H. This is a positive value for our delta H, which means that this is going to be an endothermic reaction. So now with endothermic reactions, when you add heat or you increase the temperature, you're going to shift it to the right, and your K will increase. Now, similarly, if you have an endothermic reaction and you lower the temperature, so you're decreasing the temperature, you're going to shift the reaction to the left, and this is going to cause K to decrease. And then in the reaction of 2 sulfur dioxide reacting with oxygen to form 2 sulfur trioxide, our delta H is negative 198 kilojoules. So we have an exothermic reaction. And when we increase the temperature of an exothermic reaction, this is going to shift the equilibrium to the left, and when we shift the equilibrium to the left, K will decrease. When we remove heat or we lower the temperature on an exothermic reaction, this is going to shift the reaction to the right, and that is going to cause K to increase. I will talk about the other 2 changes in a second video.